Welcome to The Explainer. Today we are diving headfirst into an absolutely wild David versus Goliath story. It's about a tiny AI model that just pulled off something most people thought was literally impossible. We're looking at a brand new research report on a model called VibeThinker-3B, and honestly, it is completely rewriting the rules on what small language models can actually pull off.
Here's our roadmap for today. We're going to cover David versus AI Goliaths, check out the spectrum to signal recipe, look at refining the reasoning engine, break down the test time CLR boost, see how it's beating the benchmarks, and finally, discuss what this new AI paradigm really means for us.
All right, jumping right into Section 1. David versus AI Goliaths, challenging the Titans.
Now, to really appreciate the breakthrough we're talking about, we have to ask ourselves, does bigger always mean better when it comes to complex AI reasoning? Because, let's face it, we've basically been conditioned by the tech industry to believe you absolutely need these massive, trillion-parameter giants to solve tough logic puzzles. The standard narrative is that scaling up, just throwing more compute and more parameters at the problem, is the only path to frontier-level reasoning. But, is that actually true?
To put things in perspective, think about the staggering disparity in model sizes right now. Our little VibeThinker model has just 3 billion parameters. 3 billion! Yet it is going toe-to-toe with absolute behemoths that are over 300 times its size. We're talking about heavyweights like DeepSeek v3.2 with over 670 billion parameters and Kimi K2.5 sitting at a massive 1 trillion parameters. Honestly, this shouldn't even be a fair fight. And yet, this incredibly compact 3B model is somehow pulling it off. So, how are they doing it?
Let's find out in Section 2, the spectrum to signal recipe, building the base.
So how exactly does a tiny 3 billion parameter model prepare for a fight that is so far above its weight class? Well, the researchers didn't just throw a mountain of raw data at it and hope for the best. Instead, they engineered a highly orchestrated, multi-stage training pipeline. This is what transformed a basic foundation model into a total reasoning powerhouse. They used a very specific sequence, starting things off with supervised fine-tuning, then moving right into reasoning reinforcement learning and capping it off with instruction alignment.
The real secret sauce here is something the researchers call the spectrum to signal philosophy. Think of it like a giant puzzle. During the first phase, you don't just force the AI to memorize one single way to solve a math problem. Instead, you show it the entire spectrum of diverse, valid methods to reach a solution. You really encourage it to explore its options. Then, in the second phase, you use reinforcement learning to amplify the signal, meaning you strongly reward the specific paths that use the most solid, rigorous logic.
Let's break down how that supervised fine-tuning curriculum actually builds up. It's a clever two-step approach. First up is broad coverage. The model learns across math, code, STEM, and general chat, getting a really solid baseline. But once it has that, they do something completely fascinating. They systematically filter out all the easy problems. Gone. The second stage forces the model to focus exclusively on brutally hard reasoning traces. We're talking problems that require thousands of tokens of deep, complex logical derivation.
Moving on to Section 3, refining the reasoning engine through reinforcement learning.
Now, the model gets subjected to some rigorous policy optimization across 3 very specific domains. First, there's Math-RL for symbolic derivation. Next comes Code-RL, and here the answers are actually run in a sandbox to guarantee the executable logic is totally flawless. Finally, STEM-RL kicks in for cross-domain scientific reasoning. But wait, here is an absolutely crucial detail. They run this entire training within a massive 64K context window. Why? Well, if you use a short window, you accidentally chop off the model's complex reasoning traces. They needed to preserve all of its deep, sprawling thoughts without abruptly cutting them short. And during the long to short Math-RL subphase, something super interesting happens. At first, the model is totally allowed to ramble. It can explore long, winding paths just to eventually hit the right answer. But in this phase, it literally trains the model to drop those redundant thoughts. It actually rewards the model for getting straight to the correct answer faster, heavily optimizing its token efficiency. Basically, it teaches the model not just to be smart, but to be incredibly concise.
To lock this whole pipeline in, they use offline self-distillation. They take all the absolute highest quality successful reasoning paths the model just figured out, and they feed them right back into the model to consolidate those new skills. After that, it goes through Instruct-RL. This is super important because it ensures that despite being this deep-thinking math and coding wizard, it still behaves like a helpful, everyday assistant that strictly obeys complex user commands and format constraints.
All right, Section 4, the test times CLR boost, scaling and inference.
So, before we get to the final battle results, there is one more trick up their sleeve. And this doesn't happen during training. It happens right as the model takes the test. It's called CLAIR, or Claim Level Reliability Assessment. Imagine the model acting as its own ruthless, strict editor. Instead of rereading its entire verbose scratchpad to verify an answer, which, let's be honest, just wastes time and compute, the model extracts a few specific, hypercritical logical claims. It specifically hunts for logical flaws at these crucial anchor points. If the anchor logic holds up, boom, the answer is pushed forward. Okay, so what exactly happens when you combine that highly trained 3B model with this CLR self-verification trick? Well, with CLR engaged, VibeThinker-3B hits an absolutely mind-blowing score of 97.1 on the AMY 26 math benchmark. Just for some context here, AMY is a brutally difficult competition math exam. Hitting anything over a 97 is straight-up frontier-level territory. It's wild.
Which brings us to Section 5, beating the benchmarks, the giant slayer in action. When we analyze the performance on the IMO answer bench, which consists of International Math Olympiad-level problems, the parameter efficiency is just remarkable. VibeThinker-3B is sitting comfortably in the frontier score band, rubbing shoulders with giants like DeepSeek v3.2, GLM5, and Kimi K2.5. It is achieving the exact same tier of elite, top-level logic, but as a tiny fraction of their size. It's an incredible achievement.
And its dominance isn't just limited to math competitions either. The numbers are staggering everywhere. It scores an 80.2 on LiveCode bench. But even crazier, it achieves a massive 96.1% pass rate on entirely unseen, out-of-distribution LeetCode programming contests. Think about that. It wasn't just memorizing old tests. It was actively solving brand-new algorithms at a rate matching top industry models like Gemini 3 Flash. Plus, that 93.4 on IFEFAL proves it can do all of this heavy cognitive lifting without ever losing its ability to follow simple formatting instructions.
Finally, Section 6, a new AI paradigm, the decoupling of knowledge and logic.
These benchmark-shattering results actually lead the researchers to propose something they call the parametric compression coverage hypothesis. Yeah, I know, it's a big, clunky term, but the underlying concept is beautifully simple. It essentially suggests that verifiable reasoning, like solving a dense math puzzle or writing complex code, is a parameter-dense capability. It's like a compact logic engine that can be highly compressed into just 3 billion parameters. On the flip side, general open domain knowledge, like knowing the capital of every country or reciting deep historical facts, is parameter expansive. That requires massive parameter coverage, acting much more like a giant sprawling encyclopedia.
Historically, the industry has treated small models as cheap fallbacks, right? Basically what you use when you simply can't afford to run the big model. Well, VibeThinker-3B proves this assumption completely wrong. Developing compact 3B models is now officially a parallel track to advanced AI. It proves that raw size just isn't the only way to achieve deep, verifiable logic. By decoupling that pure reasoning ability from encyclopedic knowledge, we can actually build specialized, elite logic engines at a fraction of the cost.
So, I want to leave you with this provocative thought as we wrap up. If this 3 billion parameter David can slay 1 trillion parameter Goliaths in pure reasoning today, what on earth happens to the entire technology landscape tomorrow? Seriously, what happens when you don't even need a massive server farm to do complex scientific reasoning or to write flawless code? What happens when that level of frontier logic can run entirely locally, right on the phone in your pocket? It changes absolutely everything. Thanks for joining me on this explainer. I really hope this sparked your curiosity as much as it did mine. Catch you next time.